Welcome. We're going to take a look at Chapter 8, Section 2, AP Calculus. Here we're finding the area between curves, and really simple formula. This is probably not going to be a hugely demanding section, but there are a couple little twists and turns. So let's take a look. Definition. If we have two functions, and one of the functions is always at least as high as the other function throughout some interval, then the area region between the curves on that interval from A to B is the integral of the first function. That's like our top function minus our second. Oftentimes what we want to do is find the area between curves on a closed interval. It wouldn't have to be a closed interval. For instance, if this is F1, I'm going to make this one F2, I'm going to make this one F1. At this point, F2 is above this point, is above F1. Now F1 is above, and now F1 is below. So if I wanted to find the total area, let's say from here to here, then I would have to find the area inside of here with F1 on top, and the area in this interval and this interval with F2 as my first function. But oftentimes we just go from, let's say this is A to this is B, in which case we just have one integral to find. And this is well worth looking at. We're going to apply most of this as we go through. It talks about calculator approaches. A lot of this might fall back on just some algebra information. What we have to do oftentimes, we have to find these points of intersection. And if we're going to find these points of intersection, we have to set the first function equal to the second function and solve in that case. So we're going to be doing all of this as we go through these examples. So let's get started. All right, hope you're enjoying your break. If you take a look at this, we're going to be back at it real quickly here. Find the area between the given curves. Now, they either need to give us an interval, or they should say something about the area enclosed between two curves. This is just a little abbreviation here. We could go straight to graph on this. I'm going to go straight to, let's find out where these intersect, because that's what we're looking for, the area between the curves where they intersect. So they intersect when 3x plus 7 is equal to x squared plus 2x plus 1. Quadratic. So we pass this on to a second semester Algebra 1 student, and we get x squared subtract 3x minus x subtract 7 minus 6 factor x minus 3 times, whoops, x, having trouble with my x's here, plus 2 equals 0. After we factor, it only takes a second. There's my x squared, minus 3x's plus 2x is good, minus 3 times 2, good. So x is 3, and x is negative 2. And it's not critical, truthfully, at this point, that we go ahead and find the exact y locations of those, but I'm going to do that. I'm going to put 3 in. When I put in 3, I get 9 and 7, 16. Double check that. When I put in 3, I get 9 and 6, 15, and 1, 16. And then I have another point of intersection. Put in negative 2. I get negative 6 and 7, 1. Put in negative 2, I get 4, minus 4, plus 1, 1. Put in negative 2, excuse me. Put in negative 2 and got out 1 in both cases. Only reason I'm doing that is I just thought, for the sake of this problem, it'd be nice to take a look at the picture. What we might do at this point is just say, well, let's find out what's happening on which of these functions is the top function. So I'm going to go negative 2 to 3. I might call this y1 and y2. And since 0 is right in here, I know they intersect at negative 2 and 3. Since 0 is between those, if I put in 0, I get 7. If I put in 0, I get 1. So in this interval, y1 is our big function. So I have to find the integral from negative 2 to 3 of y1, 3x plus 7 minus y2, x squared plus 2x plus 1 dx. But I'm going to go ahead and graph this again just for the sake of it. It helps to kind of know that we go as high as 16 here. We don't go right and left very far, and we don't go down at all. see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this one, I put in 0, I get out 7. And from there I know it's a line up 3 over 1, up 3 over 1, up 3 over 1. Eventually I get to up 9 over 3. And I also know it's going down 3 over 1, down 3 over 1. That gets me to this point right here. So there's our first line. Our second one is a parabola, and if you note, this is just x plus 1 squared. That's plain old parabola just to the left 1. So it looks like this. Goes over 1, up 1, over 1, up 1, over 2, up 4, and over 3, up 9, over 4, eventually up 16. So there we go. We got it. So there are our two curves if we were to sketch this out. And we're looking for that area. Okay, so let's do a little algebra here. Simplify inside of here. I've got a negative x squared. I've got a 3x minus 2x's plus an x. I've got a 7 minus 1 plus 6 dx. And we could integrate that, no problem. So we get, put in, oh, before I put them in, I'm going to go ahead and integrate it. I get negative x cubed on 3 plus x squared on 2 plus 6x from negative 2 to 3. So we get negative 3 to the third on 3 plus 3 squared on 2 plus 6 times 3 minus negative opposite of 2, negative 2 to the third on 3 plus negative 2 squared on 2 plus 6 times 2, and we wind up with, at this point, 125 sixths. After we go through all the calculations on that, and that would be a good time for us to grab our calculator, and I'm going to go ahead and darken this so we can see. And let's go ahead and go Math 9 FN int. I'm just going to go with my original function right here, my original integral, negative 2 to 3 negative x squared plus x plus 6 dx. Enter math fraction, and there we go, 125 on 6. So there you have it. That's pretty much the process that we're going to be utilizing. We got a couple more examples for you. Okay, example 2. In this case, we'd like to solve for y, and it's easy to solve for y. When I solve for y, I end up getting a y equals plus or minus square root of x plus 4. And let's take a look at the graph, and then let's consider our options on this. First off, the first equation could be y equals negative x plus 2. Easy enough. So let's take a look at what we've got here. So that would be y-intercept 2, slope negative 1. And by the time I'm over here, I'd be there. Okay, so we've got this. Thing go out as a terrible line. Oh, embarrassing. I almost start the video over for that, but I'm not going to. This looks just like a plain old y squared parabola, except it's to the left 4. Okay. Let's take a look. See if that makes sense. I put in 0. I get out negative 4. Okay. It'd be like doing this. Y squared equals x minus 4. It looks like plain old y squared, except That's a plus. It would be to the left 4. Okay, so that would be up 1 over 1, up 2 over 4. Looks something like this. And then we're 2 and 4. We'd have a point here. And let's take a look. We'd be down 3. That would be over 9. And sure enough, I think that would get us, by the time we're 3, we're down 2. We're down 2 more. Oh, that's just right there. Yep. That line was even worse than I thought. I think we're going to have an intersection point there. So anyway, I think our graph looks like this. And we're going to come back and talk about that graph in a moment here. But let's go ahead and find some solutions to this thing. It's easy to solve this for both of these equations for x. So I get x equals 2 minus y. And I'm going to solve these simultaneously. So 2 minus y is y squared minus 4, where 0 is y squared plus y minus 6, almost the same function we just dealt with. And I get y plus 3 times y minus 2 equals 0, or y is negative 3 and y is 2. So my points of intersection of the curve would be something negative 3 and something 2. I'm going to put negative 3 in for y right here, and I get 5. 5, negative 3. What I was trying to allude to here with my horrible graph, apologies there. Put in 2, get 0. There's my second. Put in 2 for y, get out 0. So integration, what I could do is this. I could say under this curve and above that curve, where this would be the positive square root we get when we solve for y, this would be the negative square root we get when we solve for y. Find that area, and then find this area. But the area, so embarrassing, the area wouldn't change if I tilted this and treated it this way. So what I'm saying is we're going to integrate this on y. So I want the integral as the y values go from negative 3 to 2. I'm going to treat this as my top function, and my top function is x equals 2 minus y. So we're doing this kind of sideways. And then subtract my bottom function, which is this. And we're going to have a very, very similar problem, maybe the same even answer as what we just had, but definite twist to this, literally a twist. Okay, so what do we get? Pass it off for some algebra help. I've got a negative y squared, I've got a minus y, and I've got a 2 minus negative 4, a plus 6 dy. So I end up with negative y to the third on 3 minus y squared on 2 plus 6y as y goes from negative 3 to 2. And a lot of familiar values here. Put in 2, negative 2, the opposite of, let's start that over. Put in 2, the opposite of 2 cubed on 3, minus put in 2, 2 squared on 2, plus 6 times 2, minus put in negative 3, the opposite of negative 3 cubed on 3, minus negative 3 squared on 2, plus 6 times negative 3, and let's just go straight in and take a look at what we just had here. If I go back to this, what were we dealing with? I'm just going to edit this one, because everything's really pretty much the same. It's just we got some signs that change. I'm just going to start fresh. Clear. So let's go math 9. We're going from negative 3 to 2. I can't tell my calculator to put y's in, but it doesn't matter. I'm smarter than my calculator, just not as quick. I get the opposite of x squared minus x plus 6, in this case dx, but we know we're really dying it. And there we go, our same answers we just had, 125/6. Okay, well, that's that for example 2. Let's take a look at example 3. Here's another one. We have abbreviated instructions. This should say, find the area between the curves from 0 to pi. Well, let's go ahead and take a look at the solutions of this, where they cross. Cosine squared x equals 1, therefore cosine of x equals plus or minus 1. Well, cosine of x is plus or minus 1. If we're just dealing from 0 to pi, x, it happens, because here's the graph of cosine from 0 to pi. It's 1 at 0, and it's negative 1 at pi. So that's 0 and pi. So, good news. Our intersection all occurs, or we're bound between those right where we would want to be. Here's y is 1 from 0 to pi, and cosine. Now, cosine from 0 to pi wants to look something like this, but when we square it, that changes things. We're going to come down, we're going to hit 0, and we're going to head back up. We're going to actually look something more along the lines of this. You can put it in your calculator to get a good feel, but the important thing I know is that the cosine graph, my cosine squared graph, is underneath 1, and it's all within, it never crosses over that. Therefore, I can just say integral top function minus bottom function dx from 0 to pi. And we look at 1 minus cosine squared, and here's my thought bubble on that. Well, 1 minus cosine squared is sine squared of x. So that seems like that should be easy enough. So we get sine squared of x dx. And we say, well, we just integrate that. How do we get to sine squared? We do not have a direct avenue to that. Therefore, new thought bubble here. This is a power reducing. This is half angle. I'm not crazy about the sine squared. Sine squared of theta, sine squared of x, or sine squared of theta, if we wanted to work in theta, is equal to 1/2 minus 1/2 cosine of 2 theta. That's going to be one probably for us to memorize, have access to in our calculator. So I'm going to make this a little bit uglier for a moment, but we can at least get through it with integration. So I've got 0 to pi, 1/2 minus 1/2 cosine of 2 theta. Now I have seen this happen. Because we change from here to here, some people kind of interpret, and we're in calculus, they say, oh, the integral of this is this. Nope, this is that. We still have to integrate that. So what do I get? I get 1/2 x minus, let's see, 1/2. What derivative would get me to cosine of 2 theta? Well, sine of 2 theta would, but the derivative of sine of 2 theta is cosine of 2 theta times 2. I have to cancel that times 2, so I need another 1/2 here. That is from 0 to pi. Or I get 1/2 x minus 1/4 sine of 2 theta from 0 to pi. All right, let's take a look. Put in pi. I get 1/2 pi minus 1/4 times sine. I shouldn't have thetas here. These should be x's. This is x. I got off track with my formula. Put in pi, and I get sine of 2 pi. Sine of 2 pi is 0. Then I get minus. Put in 0 here. I get 0 minus sine of 0 is 0. So we just end up with pi on 2. And that would be a good time to go to your calculator, check your calculator. But that is it. Here is your assignment from section 8.2. Good luck with that. Come in if you have any questions. We'll be quizzing it soon.